Euler's method is a numerical way of approximating function values of particular solutions to differential equations. What we need is an ordinary first-order differential equation where the derivative is a function of x and y, like x minus y is equals dy dx. We also need to know a starting point, an initial value. So this says when x is -1, y is equal to 2. Euler's method will help us estimate what y of 0 is. So what we'll do is we'll start at the point -1, 2, and then we'll use the derivative formula here, because remember, dy dx is the slope. Slope measures how much y changes as x changes. We'll use this to calculate the slope at the particular point. And then somebody will dictate to us how far we move in the x direction, and we'll use that to estimate how much y changes. And since we know how much y changes and where y used to be, here it started at 2, we'll know where we ended up. So we'll do this with a few examples here. Here is our first attempt. We're going to do a step size equal to 1. So for starting at -1, we do a step size of 1. We'll end at 0, which is where we wanted to estimate things. At the point -1, 2, the derivative will be -1 minus 2, which is -3. So what we'll do is we will travel for 1 unit in the x direction along a line of slope -3. And that will bring us down to the point to the y value -1 when x is equal to 0. Now observe, the change in y here is -3, which is precisely our step size multiplied by the derivative. Okay? Let's suppose our step size was 2. If our step size had been step size of 2, we would have gone down -3 twice, so we would have gone down by 6. On the other hand, if the step size is a half, we only go down by half of the slope, so we'd only decrease by 3/2. We'll adjust h here in just a moment. Now let's do it if it's 0.5. So as we mentioned, we know the derivative at -1, 2 is -3. So we're going to travel along a line of slope -3 for half a unit, and then we're going to stop. Well, the question is, where do we stop? We have moved 0.5 units to the right. Our slope is -3, so we're going to multiply our slope by 0.5. We went down by -1.5. We started at 2, went down by -1.5. So my new y value here is 0.5 to -1.5. Now we're going to pause and we redirect ourselves. We say, well, wait, what ordered pair am I at now? I'm at the point x equals -0.5, y equals 0.5. If x is -0.5 and y is 0.5, x minus y will be -0.5 minus 0.5, which is -1. So what that means is we're going to travel along a line of slope -1, doesn't quite look like one, but it is, for half a unit again in the x direction. Well, once we do that, we are now at 0, and we can see that we land at y equals 0. Are we sure about that? Well, let's just check it out. I think we land at y of 0 is 0. Is that correct? Our slope, y prime, is -1. Our change in x is 0.5. So our change in y is going to be the slope, y prime, at -0.5 multiplied by 0.5. So that's -1 times 0.5, which is -0.5. We started off at the ordered pair -0.5, comma 0.5. If we go down by -0.5, sure enough, we end up at 0. So we're going to illustrate this one more time with an even smaller value of h. And so this table of values gives us an inkling of what's taking place. We start here at -1. When x is -1, y is 2. we calculate our slope using the formula y prime equals x minus y. In our case, x minus y is negative 1 minus 2, which is negative 3. So we're going to travel along a line of slope negative 3 for the prescribed length of time. Well, we're doing step size of 0.2. From negative 0.1 to negative 0.8 is the 0.2 step size. Now what we would do is we would take our new ordered pair, which happens to be, well, how are we going to figure that out? When x is negative 0.8, turns out we went down by negative 0.6, so we're now at 1.4. 2 minus 0.6, so 1.4. Now we're going to take the difference in the x value and the y value. X minus y is negative 0.8 times 1.4, or minus 1.4, which is negative 2.2. We're only moving by 0.2 in the x direction. We're taking 5 steps to get there. If you multiply negative 2.2 by 0.2, we end up with negative 0.44. So we move along this line of slope negative 2.2, 4.2 units, which ends up here. Well, where were we? We were at a y value of 1.4. If we subtract 0.44, we end up at 0.96. We do this once again. Our slope, we need to figure that out next, is x minus y. Negative 0.6 minus 0.96 is negative 1.56. So we move along the line of slope negative 1.56 until we've moved 0.2 in the x direction. We go once again. Then we're going to take this negative 1.56, multiply it by 0.2, the step size, and we get negative 0.312. Repeat. Move along the line of slope negative 1.48. Then we move along a line whose slope is negative 0.63. And when we do all these calculations, we end up at our final destination, whose y value is 0.31072. So it's kind of a sophisticated thing, and like in all things calculus, if you want a better approximation, you take smaller and smaller step sizes. We've demonstrated how to use it, and this is a more formal step-by-step process of how to use Euler's method. So suppose we're given a differential equation, dy dx is some function of x and y, and we're given some sort of initial condition. When x is x0, y is y0. So the point x0, y0 is on the graph. Somehow the step size will be given to us. Either they tell you, hey, let's let h be 0.25, or they'll say use a certain number of steps. From that, you can determine what the step size is going to be. For example, if I'm moving from A to B, and I'm supposed to use n steps, then the step size would be b minus a over n. Very similar to what you may have used when you were doing Riemann sums. So what I like to do is then, we're starting at x0. I like to make a little chart. You start at x0, and then you add h to your previous x value. That would give us x1. And then if you add h to x1, you get x2, and so on. Calculate your slope at the initial value, which will be essentially finding the expression evaluated at x0, y0. Whatever that slope is, multiply it by your step size. The reason we're doing that is because the slope of any line is a measurement of how much y changes as x changes. H is measured in whatever the units of x are. So we'll multiply those two together. This will tell you how much y changes by over that first interval. Then you find y1. Since we know how much y changes by, we'll add y0 to that particular change. We multiply those two together, remember. That will be y1. And then we keep doing this until we reach our desired value. Okay? So here is an expression, once again, that represents what h is equal to. So here's our first example. And let's see here. So dy dx is xy squared, y of 0 is 3, and we're going to use Euler's method with 4 steps to estimate what y of 1 is. Okay, 4 steps. We're starting at x equals 0. Okay, if we end up at x equals 1, we take 4 steps, it's pretty easy to see that your step size will be a fourth, or 0.25. So what I'm going to do is I'm going to make a table of values. I make the table in what I feel is the most logical sense. We're going to put x here, then we'll put the y value. From x and y, I can figure out what y prime is, the derivative. From y prime, I can figure out what delta y is. In our case, it's going to be whatever y prime was multiplied by 0.25. I don't have a lot of room there for that. And then, once we know that, we're going to be able to calculate our new y value. Our x values start at 0. They go up by 0.25. So if I go up by 0.25 again, I'm at 0.5, then 0.75, and then 1. I'm going to write the calculations at the bottom. I will erase them as I go. So we knew that when x was 0, y was equal to 3. So y prime is supposed to be, or we say dy dx, it's x times y squared. Our x is 0. So we're going to multiply 0 by y, which it doesn't matter, but by 3 squared, which is 0. So y prime is going to be equal to 0. Then I multiply delta y by y prime. Or by, to get delta y, I multiply y prime by 0.25. Let me write this slightly differently. 0.25 y prime, which is 0.25 times 0, which will be 0. So our change in y is 0, which means our new y value is the old one plus the change in y. Well, our old one was 3, which I get from the table here. Our change in y is 0, so 3 plus 0, which is still 3. Okay, now it's about to get a little bit more exciting. So let's figure out what y prime is here. Y prime will be x times y squared. X, in our case, is 0.25. Y squared is 3 squared. Y is 3 still. 9 times 1/4 is 9/4, which is 2.25. So that's going to be what, I forgot my little prime there, that's what y prime is, 2.25. To figure out what delta y is, we're going to multiply 2.25 by my step size, 0.25. I'm on a line of slope, 2.25. I move 0.25, and that gives me the change in y. 0.5625. Okay, now it's going to get messy here because our numbers are getting big. We're going to take our old y value, 3, add it to the 0.5625. So that's pretty easy to calculate. That's 3.5625. Now we're going to take the difference in x and y. We're going to take x, I'm sorry, not the difference. That was the previous example. We're going to take y prime, which is x times y squared. When we do this, 0.5 multiplied by 3.625 squared gives us this 6.34 number. Then we're going to take, in order to figure out how much y changes, what delta y is, we're going to take our y prime and multiply it by 0.25. Our y prime is the 6.34 blah, 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 blah. Multiplied by 0.25 gives us this crazy number. We fill these values in the table. Now we're going to add 3.5625 to 1.586, yada, yada. It's the old y value plus the change in y, which equals 5.1489 and so on. Once again, we do all that business again. Our differential equation is x times y squared, so we're going to multiply 0.75 by this new y value squared. When we do that, we end up with 19.88357753. Once we have that value, we can then substitute it, or not substitute it, multiply it by 0.25 to figure out how much y changes by. And when we multiply 0.25 by that, we end up with 4.970894391. So let's fill that in. And for our final step, we will add the old y value and the change in y. And when we do that, we end up with 10.11982016. These problems don't get much different than that. We'll do one more example, but that should be enough to give you an idea of how Euler's method works. So this time we want to use it with step size of 0.2. We're given this step size rather than have to figure it out. We want to estimate y of 1. Y of x is the solution to the differential equation y prime equals 2xy plus 1, where y of 0 is 2. So let's set up our chart. Just as before, we have a row for x, a row for y, a row for y prime, which is a new formula here, the 2xy plus 1, and then delta y, which is now 0.2 times y prime. We'll go ahead and fill in the x values. Remember, they start at 0 and go up by 0.2 each time. And now let's fill in y of 0, which we know is equal to 2, according to our initial condition here. So this will be 2. Y prime is 2 times xy plus 1, which in our case is 2 times 0 times 2 plus 1, which is equal to 1. Delta y is 0.2 times the number we just found, which is 0.2. And our new y value is the old y value, which was 2, plus the 0.2. So that's 2.2. Once again, we take the differential equation formula, 2xy plus 1, and I'm going to substitute in my new y values for that, x and y values. So y prime will be 0.2 times 0.2 times 2.2 plus 1. This equals 1.88, which we now multiply by 0.2. That's the change in x, the h value, 2 times 1.88, which is 0.376. So let's fill those in. These are easy to fill in. 3.376 here. And now we will add the old y value to the change in y to get our new y value, which is 2.576. Now we'll calculate as we did before. We're going to multiply 2 by the x value, the y value, and then add 1. When we do that calculation, we end up with 3.0608, and we multiply 3.0608 by 0.2, we end up with 0.61216. We now add the new change in y to the old y value to end up with 3.18816. Again, we're going to multiply 2 by x by y and add 1, which brings us to 4.825792. When we multiply that by 0.2, we get 0.9651584 for the bottom row. When we add that to the 3.188816, we end up with 4.1 1533184. Now, I'm just going to go ahead and put the numbers in. When I multiply 2 by 0.8 and then multiply that by that 4.15 and add 1 to it, we end up with 7.64530,944. When we multiply that by 0.2, our change in x, we get 1.529061888. And now for our final maneuver, we add the old y value to the new change in y, which gives us our final answer. I'm going to write this in green as a celebratory remark. It is 5.6823803. Now you might say, why are we doing it with so many decimal places of accuracy? I do it to all those decimal places of accuracy because if I start to round too soon, too early on, we may end up way off from the actual answer. So you want to be careful to write down as much as you can. Pay attention to the instructions that are given to you in these problems.